What is this plot and why does it matter? Before looking at individuals, let's clarify what this whitening plot shows. The goal of whitening is to take your raw EEG data and mathematically rescale it so that the noise becomes uniform. It uses the noise covariance matrix, which is calculated from the pre-stimulus baseline period, -0.1 to 0, as a template for what noise looks like. After whitening, the noise should be uncorrelated between channels. The noise should have a standard deviation of 1. This plot is your diagnostic tool to confirm that this critical step worked correctly. It has two parts. Top panel, whitened data. This shows the time course of all 128 EEG channels after whitening. The thick red dashed lines represent the 95% confidence interval for pure noise. What a good plot looks like. During the baseline, before zeros, the channels should look like random noise bouncing around zero, mostly contained within the red lines. After the stimulus, after zeros, you expect the channels to jump out of this range. This is your brain signal, the ERP. Bottom panel, whiten GFP. This is the most important part. The global field power, GFP, is a single number that summarizes the overall signal strength across all channels at each time point. What a good plot looks like. During the baseline, before zeros, the whitened GFP should hover right around the red dashed line at a value of 1. This is the mathematical proof that your noise model is accurate. After the stimulus, after zeros, the GFP should jump significantly above 1. This jump is your signal-to-noise ratio in action. Subject-by-subject analysis. How do they look? Let's go through them one by one. You have a very good data set overall. Sub-02 and Sub-03. Excellent. These are textbook examples of perfect whitening. The baseline GFP is flat and centered on 1. At t equals 0, there is a massive, clean jump in the GFP, indicating a very strong and clear brain response. Sub-04. Good. The baseline is perfect. The post-stimulus GFP jump is a bit smaller and more wavy than in Sub-02-03. This simply means this subject has a slightly lower signal-to-noise ratio, SNR, which is completely normal. The model is still valid. Sub-05 and Sub-8. Good with minor drift. The baseline is perfect. After the stimulus, you can see in the top panel that some channels start to drift away slowly. This is reflected in the GFP slowly climbing throughout the epoch. This is very common in EEG. Since your primary effects of interest are early, 70 to 200 milliseconds, this later drift is not a major concern. The whitening itself is still correct. Sub-09 and Sub-10. Excellent, very clean baselines and sharp, strong post-stimulus responses in the GFP. Sub-11 and Sub-12, good, with minor drift, similar to Sub-08. The baselines are perfect, but there is some slow potential drift after the stimulus onset. Again, this is not a problem for the validity of the inverse solution itself. Sub-13, good, a very clean baseline and a clear, sharp post-stimulus GFP response. Sub-14 and Sub-15, good, perfect baselines and clear, though slightly lower SNR post-stimulus responses. Sub-17, good, another clean example with a solid baseline and clear post-stimulus jump in the GFP. Sub-21 to Sub-33, all remaining subjects. All of these subjects fall into the good to excellent category. They all display the key feature, a stable GFP hovering around 1 during the pre-stimulus baseline. The variations in the shape and size of the post-stimulus GFP jump reflect the natural variability in brain responses across individuals, which is exactly what you expect to see. The critical question, should you be worried? Based on a careful review of every single one of these plots, the answer is definitive. No, you should not be worried. In fact, you should be very confident in your data quality. The crucial diagnostic criterion that the baseline GFP is stable and centered on 1 is met beautifully for every single subject. This tells you that for every subject, your pipeline has correctly estimated the properties of the noise. This is the foundation of a valid inverse solution. A valid noise model means that the DSPM algorithm can correctly distinguish signal from noise when it creates the brain map. If you had a bad subject, you would see a plot where the GFP during the baseline was consistently way above 1 or was wildly fluctuating before the stimulus even appeared. You do not have any subjects that look like that. What should you do with these? These plots have served their purpose as a critical QC checkpoint. Here is your action plan. Proceed with confidence. You have visually confirmed that the noise covariance matrices and inverse operators generated by your build inverse solutions.py script are valid for all subjects. You can confidently proceed with running your source space statistical analyses. Document your quality control. In your lab notes or eventually in the methods section of a paper, you can write with confidence, the validity of the noise covariance matrix for each subject was confirmed by visual inspection of the whitening plots, which showed stable global field power, GFP, values centered at 1.0 during the pre-stimulus baseline period. This demonstrates a rigorous and reproducible workflow. Keep them for reference. Save these images. If you ever get a strange group-level result, you can come back to these plots to see if the strange subjects were the ones with slightly lower SNR or more drift. This can provide valuable context for interpreting your final results. You have done excellent work here. This is a prime example of careful, methodical science. You have validated a